is lecture, welcome to lecture, I think maybe 19 or 20, day before spring break. Students are focused and ready to go. We're going hard this whole period, so just don't even try to fake out any kind of...
Did you get a haircut?
I did get a haircut. Looks great. Alright, good. So, yeah, it was getting ridiculous. So, we are going to talk about today this thing which goes by various different names depending on who you talk to. Rectilinear motion is what some people call it. You could also just chill. We're doing everything. It should be great. So this is one-dimensional motion, or motion in one direction, or rectilinear motion, whatever you want to call it.
Oh, that was yours?
Alright, so...
Never told me.
Ron, stop talking.
Sorry.
Alright, so the idea is that we have a number line, and there is a 0 point on this number line. Is someone paying attention? Yeah. And we have some object which is moving back and forth along this number line. So what we're going to talk about for the next half an hour is another application of differentiation. And particularly, specifically, the application of differentiation that we're talking about is the same old example which motivated this entire thing, which is motion. So we're going to be talking about velocity and acceleration and everything like that. So, and to keep things very, very simple, we're going to imagine that there's an object, and this object is simply moving back and forth along a number line. So we have the and there's numbers on this number line, like real numbers. And so at any given point, the object, well, I don't know, do you have a particular favorite object?
Your new
Bear.
Hair. Your new hair.
Bear.
No, your new haircut. Just the outline of it.
Bear. Is a bear on like a bicycle or anything, or just a regular bear?
Just a regular bear.
Okay, so it's just a regular bear. Alright, so there's a bear which is running back and forth along this line according to some sort of pattern. At any given moment, the bear is to be found at a certain spot on the number line. Yeah? So, we have a position function, and position is usually, we usually use an S for position. And what we have is a position function based on time, and the position function simply outputs, for any given time, the position of the bear. And the bear might be over here. This is kind of like positive land. This is where the position is positive, and this is where the position is negative. So this, of course, assumes that you have set up some sort of coordinate system in which you have a 0 point in a certain direction is positive, certain direction is negative. Okay, that is great. Oh, also we assume the times are going on from like negative infinity to infinity. So this bear is the infinite bear. All right. Then we have velocity. And velocity is defined to be the derivative of position. So the derivative of the position function is velocity, derivative with respect to t. Okay, and that's kind of like what we'd already talked about this, so we're just talking about it again. And lastly, acceleration. Well, acceleration is the rate of change of velocity. So it's s double prime, which is just v prime. So this is just the acceleration function. Okay, cool. All right, so now, all the things that we're about to do are essentially just physics, but they are sort of careful physics done with, we're using calculus to do physics sort of properly. I have a piece of paper somewhere that I lost. Great. All right, whatever, I can just wing it. We have to be very careful. We have to be careful, to some extent we have to be careful because velocity is a very technical term, and the word that we normally use is speed. But there's definitely a difference between velocity and speed. What is the relationship between velocity and speed, actually?
Velocity is sign.
Velocity is signed, yeah. So velocity can be negative, and actually maybe we should talk about that. When is velocity negative? Or what is the significance, Eric, what is the significance of velocity being negative? Think it out.
You're like going backwards.
Yeah, pretty much. Why? Raymond, explain why.
We generally consider forward positive, so we're going the opposite of positive, so it's negative.
I don't think I like that answer because, okay, that's fine, you're both right. But actually I can explain why that's so, because note that velocity is not just some new concept I'm introducing, it is being defined explicitly as the derivative of position. So if my velocity is negative, let's just say, if my velocity is negative, the significance of that is that the derivative of position is negative. Okay, in other words, what do I know? If the derivative of position is negative, what can I say about position?
Your change in position is
My change in position is negative, or even another way of saying it?
Position is decreasing.
Position is decreasing, yes. Yes, we have, and you said that too, I know, but you whispered it, so sometimes I ignore you when you whisper. But yes, yes, the derivative, if velocity is negative, if the derivative of position is negative, then that's just another way of saying that the position is decreasing. And since the position we think of as being a number, if the position is decreasing, it means the position number is getting smaller. If the position number is getting smaller, then we're moving to the left. Okay? So it's not just arbitrary that we decide that velocity means moving to the left and negative and positive velocity means moving to the right. It follows from our definition of velocity as the derivative of position. Is everyone with me? All right. And okay, so let's just like do some combinations. Tell me, let's do, okay, so if the velocity is negative and the position is also negative, please describe in words, normal words, like what's going on there. Just like, I don't know, someone. Rohan, talk to me.
It's behind where the zero mark is, and it's continuing to go further in that negative direction.
Yeah. Yeah, we can say that if the position is negative and the velocity is also negative, it means we are on the left and we are also moving left. You guys okay with that? I mean, there's a bunch of different ways to say it. What he says is fine too. All right, what if my velocity is negative and my position is positive? Someone else, Gerhard.
You're on the right.
Yeah, on the right. And you are moving left. Okay, what else we got? If my velocity is positive and my position is positive, Kendall, what's going on?
And the position is positive. We're on the right, moving right.
On the right, moving right. And the last one, if my velocity is positive and my position is negative, Daniel, what's going on? In the negative land and moving right. Yeah, I agree. You are on the left, moving right. Okay, so that's kind of cool. So now I can ask kind of interesting question. When am I moving towards the origin? Towards the origin. Magna.
When S and V are opposite signs.
Yeah. When S and V are opposite signs. Have opposite signs because essentially I'm moving towards the origin when I'm either on the right moving left or on the left moving right. Right? And so it's sort of like when I'm moving towards the origin when the velocity vector is pulling me in the opposite direction of the position vector, right? That's kind of how I think about it. I'm on the right, but I'm moving left, it means my velocity is the opposite side of my position and same, okay, cool. And then when am I moving away from the origin? Just shout it out.
When they're the same sign.
Yeah, when they have the same sign, right? When S and V have the same sign. Because, yeah, I'm moving away from the origin when I'm either on the right moving right or on the left moving left, right? So when the velocity and position vector are pointing in the same sign, or pointing in the same direction. Okay, cool. So that is all nice and pretty easy, I guess. Although some thought is required. But one problem, I think when we start to get acceleration into it, it gets more complicated. And that is because, well, it's again back to this same issue, which is that these words have technical meanings and then they have these like loose informal meanings. So even velocity, I mean, people just generally don't, outside of physics, people don't generally use the word velocity. So for example, like when you drive around, and you see on the road speed limits, not velocity limits. For example, Ethan, you can't try this trick, it doesn't work. If you are, suppose you're at home, right? So this is like home, and then this is like school, right? And it seems reasonable to okay, so you drive from home to school, and then you go back home again, right? So now suppose there is a 35 mile per hour speed limit. Okay. Now, in my personal opinion, if it's safe to drive 35 miles per hour, it's also perfectly safe to drive like 52 miles per hour. But not everybody sees it that way. So if you get caught driving 52 miles per hour, what you can say is, well, so I suppose I drive to school and then I'm on my way home, right? So you get pulled over and you say, well, as I have designated home to be the origin of my coordinate system, and I have already been to school, now I am on the way home. So in fact, my velocity is negative, and I'm going negative 52 miles per hour. This is well below your 35 mile per hour limit. Okay, yeah, and then the cops are right.
Also,
No, they arrested him.
It is also a speed. That's why it's a speed limit, not a velocity limit.
yeah.
I mean, I can define my coordinates however I want, man. All right, so that's the thing. Oh yeah. So throughout this subject, I never used the words casually. If I say the word speed, I mean speed. If I say the word velocity, I mean velocity. And by the way, can I get a definition of speed? What is speed? Everyone should be able to answer this.
Someone whispered it over here.
Oh, I didn't hear.
It was Raymond or someone.
This should be like everyone should know the answer to this. Ron, what's the answer?
Absolute value of velocity.
Oh yeah, that's right. Yeah, the speed function is simply the absolute value of the velocity function, like definition. Okay.
But
So what?
are you sure?
Yeah, I'm pretty
What
sure.
if you move like this way and then this way?
Yeah, it's still absolutely.
I don't understand.
Like,
So what?
if you move this
Your
way,
average
you move
velocity
this
if
way
you
and
go
this
somewhere
way.
in the
Wait.
So
what's
your
it-
average velocity if you like move from this chair to that chair, from that chair back to this chair,
Zero.
would be zero. But
Yeah.
your average speed won't be.
Yeah, yeah.
So that's not absolute value.
I didn't say that the average speed
Oh.
is the absolute value of the average velocity, but I said that the speed at a given time is the absolute value of the velocity. Okay. Good. All right. So the word, yes.
Well, you're talking about vectors. Like, what does it mean for
Sort of.
a velocity vector to act on a position vector? Because, like,
I didn't particularly say it acted on. I just
Sorry,
said.
but
In
it
fact,
kinda
I'm sort of
does.
ignoring vectors because I'm doing this only in one dimension. Though these are sort of vectors, you could also just think of them as numbers because it's just one dimension. So they're one-dimensional vectors. So thus I can kind of avoid vectors. That'll be next calculus class. Okay, Mateo. Here's the problem. The problem is acceleration. Acceleration is weird. In fact, we all use the word acceleration, and we use it in an informal sense. So when we say things, oh, it's accelerating, everyone thinks that they know what that means. The problem is that the word acceleration now has a technical meaning as the second derivative of position. So we need to see how that all comes into play, and we need to kind of unlearn certain things, commonsensically informal and hence wrong uses of these words. Okay, so let's look at a couple scenarios. Ready, Stephen? Are you pumped?
Yes.
4 scenarios. Check it out. Suppose, okay, here we go. Suppose I am going 50 miles per hour to the right, so my velocity is 50. And then, a couple seconds later, my velocity is 62 miles per hour. And a couple seconds later, my velocity is 73 miles per hour. What is the sign of my velocity? Positive. What is the sign of my acceleration?
negative.
What?
Yeah, because the first one you do 12. and then you-
No, overthinking it. What is acceleration?
Positive.
Acceleration is the derivative of velocity. It's the rate of change of velocity. It describes whether the sign of the acceleration should describe whether the velocity is increasing or decreasing. What is the velocity doing? It's increasing, so my acceleration is positive. Is everybody cool with that? Okay, more. Suppose now I am going 60 miles per hour. And then a couple seconds later, I'm going 41 miles per hour. And a couple seconds later, I'm going 35 miles per hour. The sign of my velocity, still positive, so mean acceleration, negative. Why? Velocity's getting smaller, right? Acceleration is defined to be the derivative of velocity, so it's the rate of change of the velocity. And the velocity is changing in the sense that it is decreasing. If the velocity is decreasing, its derivative must be negative. Okay, those are the easy ones which match common sense. Now it gets a little complicated. Okay, so now suppose my velocity is negative. So suppose I'm going negative 60 miles per hour. Then a couple seconds later, I'm going negative 50 miles per hour. And a couple seconds later, I'm going negative 30 miles per hour. What is my velocity?
Negative.
This is definitely negative, because like I kind of told you so. What is my acceleration? Positive.
Negative.
No, wait.
Oh,
No, positive.
Wait, we're going from right to left here,
Positive.
right? Like,
It's definitely not.
it's kind of confusing
Oh,
how
we're
you
going
draw
from right
it.
to left? No, we're going from left to left.
Wait, which way are we going?
We started here, then we
Okay.
did that, then we did
Yeah,
that.
so it's positive.
Oh.
So my acceleration is
Positive.
Positive.
positive, yeah, it is positive. My acceleration is positive. So my acceleration is positive because is the velocity increasing or decreasing? Answer. It's increasing in the sense that it is becoming less negative, right? Yet, how would I describe this in normal words if I had to, like, using simple words?
Slowing
Going
down.
backwards faster.
Slowing down. Yeah. In this case, also what Buta said too, right? We're moving to the left, slowing down. But at the moment, I just want to focus on the fact that we are slowing down. In fact, and then how about questions?
How does this like correlate with like the concavity?
Coming. That's coming or not. I don't know. Maybe. Whatever. Later. This one. Speeding up or slowing down?
Slowing down.
Yeah, slowing down, right? Here we are definitely slowing down. Here?
Speeding up.
Yeah, here we are definitely speeding up. And then the last one depicts the following scenario. I'm going like negative 40 miles per hour, then I'm going like negative 60 miles per hour, then I'm going negative 110 miles per hour. What if I'm doing that first, then that, then that? What is my velocity? Negative, my acceleration.
Negative.
Yeah, negative, right? Acceleration is the rate of change of velocity. The velocity number is getting smaller, but getting smaller in the sense of more negative. But how would you describe this in words?
Speeding up.
Speeding up. Okay, so I would like to just ban forever from this class the use of the phrase accelerating or decelerating, like banned. I would like to say speeding up and slowing down, because those are totally unambiguous, right? If someone says you're speeding up, you know exactly what they mean. And note the lack of connection, as you might have suspected, between the sign of acceleration and whether the object is speeding up or slowing down, right? They're like not linked. You can't make a really good conclusion there, because that's because we're interpreting acceleration in a very technical sense, where if the derivative, if the velocity is getting less negative, it's actually increasing, even though the speed is getting smaller. Is everyone okay with this? Once you get it, it's just like easy, but it's very confusing for some people. Okay, la la la, when am I speeding up? Say it again. Yeah, exactly. The general conclusion to draw from all this is that I'm speeding up when I'm either going in a positive velocity and that velocity is increasing, or if I'm going in a negative velocity and that velocity is decreasing. So it's when the velocity and the acceleration have the same sign. And when am I slowing down? When the opposite does, yeah. Opposite does. Because it's going to be, I'll be slowing down when I'm either going in a positive velocity and that it's getting smaller, or I'm going in a negative velocity and it's getting bigger, but by bigger we mean less negative. Cool, cool? It's really not that hard. It's like physics. Okay. Giant packets. Yeah.
Oh, is this the
Giant package. Giant you're gonna do all this, but not right now. For starters, what you're gonna do, I'm gonna do in a slightly different order this year. We are going to turn to page 7. And we're gonna do this right now. Go. For all the people on the internet, which is nobody, we are doing this packet called Applications of Differentiation 2015. Page 7.
Yeah, that is looking
Some kid in the Arabic class after we said that. So I seem to be particularly interested in when my position is positive and negative. Shape, we're doing physics. Good. And when my velocity is positive and negative.
Functions?
Yeah, no, this is calculus.
What's functions doing after break?
I see where you're going with that.
Why are you sitting in that chair? Change special? Thank you.
That what we did last time?
I got it. You want to see it? React to it.
Yeah.
I got 0.
Can I see what you did?
You
You do it 3 over 2 for E?
When S is not the derivative of S.
Right.
No, that's a different thing.
When is
Like,
like
you have to plug it into whatever this is the other object velocity.
So your position is at a minimum when your velocity is at a critical point. There's only one critical point. Yeah. Because there's only one velocity.
All right, can we do it? What I was saying just before Shaper walked in is because I'm interested in when position is positive and negative, and when velocity is positive and negative, what I do is factor position really nicely if I can, factor velocity nicely, and then make nice number lines for these things. There's like a kind of space for that on the top. So the sign analysis for the position is, well, it's like a parabola with roots at 1 and 2, so it's going to be positive and then negative and then positive. Yeah? Yeah. And then the velocity changes sign at just 3/2, and it goes from being negative to positive. So, can I go through all these now, like really fast? Or maybe I should walk around and squeeze with
You
you
guys
first.
see?
Wait, can you talk about?
Yeah, do it first, quick, before I go away the answer.
No,
That should be 9/4. Yeah.
I don't think you guys need more time. Go faster.
Wait, so what did you get?
Between like,
Alright, find the position at time 5 seconds. So basically just saying like, alright, where am I at time 5? Answer, I just plugged 5 in here, I get 25 minutes, I get 12, and the answer is my 12 meters. I think we're doing meters in seconds, right? Yeah. Okay, part B, find the average velocity, on the interval 0, 5. Well, the average velocity is just the change in position over the change in time. In other words, it's where I am at 5 minus where I am at 0 over 5 minus 0. And S of 5 is 12 and S of 0 is 2, so that difference is change is 10. So I got 2 meters per second. Is that what you got? Okay, good. And just like Emma was mumbling like 10 minutes ago, average velocity and average speed are different. Kendall, if I start at my house and I drive 90 miles per hour to the store and back again, what is the average velocity of that trip? 0, correct. The average velocity of any round trip is 0 because the average velocity is the change of position over the change in time, not the total distance over total time. That's average speed. All right. Find the instantaneous velocity of the particle when t is 4. Okay, so they're just being like, yo, what's the velocity at time 4? Answer, it is 5 meters per second. Part D, find the acceleration of the particle when t is 4. Well, the acceleration, I probably should have found the acceleration also. Let's do that. What is the acceleration? It's just 2. Producing a quite boring number line for acceleration is just always positive. So this is going to be 2, and the units are meters per second, or meters per second squared. Part E, you guys getting these all right? All right, part E, what value of t does the particle change direction? It changes direction at? Yeah, at 3/2. Because as we discussed, when the velocity is negative, the particle is moving to the left. When the velocity is positive, the particle is moving to the right. So I'm going to take a peek in there to make sure that's all like good stuff. Part F, where is the particle when S is a minimum? All right, this is a little, well, it's still pretty easy, but how do we do this?
Just plug it in. Plug in 3/2
To what?
into the position.
Yeah. One way to think about it is, there's a couple different ways to think about it. There's like a math way of thinking about it, and there's like a common sense way of thinking about it. The math way is to say, well, this is the position function. I want to know when the position is minimum, right? Or I want to know what the minimum position is. So essentially you're asking me to minimize S. Well, what do I do when I minimize S? I take the derivative, and I see where the derivative changes sign. So well, the derivative of S just is V. And so the derivative of S is going from negative to positive at 3/2, so we know that that's a relative minimum. And as the S function is decreasing from negative infinity to 3/2, and then increasing from 3/2 to infinity, that relative minimum must also be an absolute minimum. I guess getting this, I'm saying things that are important, but like not that hard. Right, that's the math way of thinking about it. The common sense way of thinking about it is, yo, I'm moving to the left for all of eternity, and then at 3/2 I turn around and start moving right again. So when am I going to be farthest to the left? At 3/2. Either way you look at it, s of 3/2 is the answer, and that is -1/4. Okay, when is the particle moving towards the origin? Right, Fleischman.
Particle is moving towards the origin from negative infinity to 1 and from 3/2 to 2.
Yeah. And the kind of way of thinking about that is, like we said, I'm moving towards the origin when I'm either on the right moving left or on the left moving right. Here I'm on the right moving left, and here I'm on the left moving right, which is why it's good to have the number lines all nice and like on top of each other like that. Cool? Okay, and then the part H is just the reverse, right? When is the part I'm moving away from the origin? Moving away from the origin when I'm either on the right moving right or on the left moving left. Here I am on the left moving left from 1 to 3/2, and I'm on the right moving right from 2 to infinity. Cool? Questions? Happiness? Okay, it is also possible to make a so-called... What's up?
Which did both of this package.
Yeah, it's pretty good, right? It's possible, Charisma, it's possible to make a snake diagram. Oh, Charisma, by the way, since you're like kind of fake Dutch and stuff,
Yeah.
we're having a Dutch party
Where?
the Monday after Wallops. Is Koningsdag. Do you even know what that is? You don't know anything. You're like when like American Chinese people go to China and then people try to talk to them in Chinese and they just look like stupid because they don't know anything. You have this. You're walking around with like the most Dutch name possible and you don't know anything. You don't even know how to pronounce your own name. What you need to do is come to Koningsdag celebration Monday after Wallops. It'll be happening in this room, 5th and 6th period. You guys know Lizzie, senior? She's Dutch. She's like real Dutch. I'm inviting. No one's watching this video. I'm inviting all of you to this party. I just ordered $55 worth of stroopwafels.
Oh, no, those things are good.
Those things are
Those
good.
things are good.
How do you know what stroopwafels are?
Because we like my mom like bought it like some like store. Like no.
Right. Okay. I think Lizzie's parents are getting her some like cheese and stuff. We're gonna make tulips. It's gonna be awesome. Okay, so that's happening. I just remembered that. All right. Anyway, Chancellor, we have to so you can learn some Dutch vocab.
Sure.
Okay, good. All right. What the hell am I talking about? Oh yeah, the snake diagram is a kind of visualization of what's going on, in which you hang on a second. Can I get some like purple markers and stuff? So what is happening? If we had to describe, where is the particle at time like -1,000,000? Like really far right. Yeah, all the way on the right. It's all the way on the right. And then what is happening is we are moving towards the origin, right? That's what you guys told me. And we keep moving towards it. What's the first interesting thing that happens? What's the first number that has appeared in the story? I would say time 1. What interesting thing is happening at